Thanks, Yu, for the kind introduction. Let me share my screen. All right. Hello, everyone. Today I'm going to present putting AI on a diet, TinyML, and efficient deep learning. So deep learning has becoming more and more accessible over the years. When deep learning first becomes applicable, those models usually require cloud servers with powerful GPUs to run. And the machines are pretty expensive, usually costing tens of thousands of dollars, and it requires internet connection to send your local data to the cloud for processing, which also triggers privacy issues when dealing with sensitive data like the healthcare data. With the advance of technology these years, people are able to dramatically reduce the cost of deep learning deployment. Nowadays, we are able to run many of the AI algorithms just locally on your cell phone, which brings the second generation, the mobile AI. By running AI algorithms locally on your smartphone, we can easily access the benefits of AI without paying extra money, and at the same time, protect our data privacy. So what's the next step of efficient AI, and how can we make AI even more accessible? So I have worked on a couple of projects toward this direction. First one is the deep compression project to make AI run fast and efficiently with limited hardware resource. The basic idea is rather than accelerating a large neural network, can we compress it and make it smaller to fit a low power hardware platform? So with deep compression, we can reduce the model size of original Resonant 50 from 100 megabytes to only 6 megabytes, so 16 times compression by pruning and quantization. And if you search the pruning and sparsity as the keyword network pruning is getting popular all the way back from 1990s with the paper Optimal Brain Damage, and then to 2015, learning both weights and connections for efficient neural networks. The number of publications grew exponentially after that to thousands of publications this year, with attracting both the hardware community and also the machine learning community to pay attention to this technique of improving the efficiency of neural networks. And we have designed a couple of hardware accelerators that impacted the industry, including the EIE, Efficient Inference Engine, ESE, the Efficient Speech Recognition Engine, and recently the Spark and Spartan, sparse architecture and sparse attention. And now sparsity is natively supported by the NVIDIA A100 GPU with 2x peak performance and 1.5x measured BERT speedup with such 2 to 4 sparsity. Beyond model compression, we also worked on AutoML and neural architecture search to automatically design compact and small models. So here we have designed 3 generations of technique, auto technique. The first generation is the AMC, AutoML for model compression, which aims at figuring out what's the optimal sparsity and redundancy in each layer, and how much should we do channel prune the channels by how much for each layer. So we use reinforcement learning to guide this process. So the reward is a combination of accuracy and the model flops. We want to encourage high accuracy and low flops. And just like AlphaGo learning to play Go, this RL agent can learn what is the optimal sparsity and redundancy for each layer. Our second generation, rather than like the first generation, which we compress an existing model to channel pruning, we want to design search and efficient architecture from scratch. Conventional method, this is very expensive, so they have to rely on proxy tasks, such as a search on CIFAR and then transfer to ImageNet, search on just one building block and then expand to the whole network. We make this process more efficient so that we can directly search on the target task and target hardware, like search directly on the ImageNet. That's why we call it proxyless neural architecture search. So in the design space, we may have many different choices for each layer, like convolution 3x3 or 5x5 convolution or density mapping or pooling. Among different choices, we give each choice an architectural parameter, which is the probability of choosing this path during the architecture search. So during the learning process, we learn not only the weight parameters, but also these architectural parameters. And in this way, we make the architecture differentiable. We can also use RL-based method to learn those architectural parameters. And this requires only 200 GPU hours to search rather than 48,000 GPU hours from conventional work. And this received the first place in the Visual Weekwords Challenge in 2019, given a peak memory usage smaller than 250 kilobytes and model size, MAC constraints are all met very closely. For human design, it is very challenging to meet different design constraints at the same time, like peak memory, model size, and max. But with such AutoML-based method, we can tightly fit all the different walls of constraints and have a high accuracy. In the third generation, we propose this HAQ, hardware-aware automated quantization, to find what is the optimal precision for each layer. Given the popularity of mixed precision hardware, this is an effective tool to automatically find the redundancy and precision for the weights and activation for each layer. So we want to move forward, and we believe that the future belongs to TinyAI. There are billions of IoT devices around the world based on microcontrollers. They are much cheaper, much smaller, and much power efficient, but they are almost everywhere in our lives. If we can enable AI algorithms on these IoT devices, we can greatly democratize AI and extend the applications of deep learning to those applications such as smart retail, personalized healthcare, smart home, smart manufacturing, precision agriculture, autonomous driving, etc. But this is extremely challenging. The amount of memory in the microcontrollers is 4 orders of magnitude smaller, 320 kilobytes compared with 4 gigabytes compared with the mobile phone, not to mention the GPUs. So the tiny model design would be fundamentally different from mobile AI model design. Since there is no DRAM of a microcontroller, and very rarely there is operating system. If there is, also occupy a lot of resource, so usually there is no more virtual memory. And so we cannot directly scale existing mobile models such as MobileNet because the weight and the parameters in that is non-proportional, as will be illustrated in the next slide. So existing MobileNet only reduces the model size, but not the activation, which is a key bottleneck for deploying AI models on microcontrollers. For example, Redshift 18 to MobileNet v2 0.75, they both have about 70% top-on ImageNet accuracy, and the MobileNet successfully reduced the parameters by 4.6 times. However, the activation size is actually 1.8 times bigger. This is super inefficient due to the inverted bottle architecture. The increase the activation is 6 times. Mobile phone, this is not an issue because there are vast amount of memory, like 4 gigabytes. But for the microcontroller, this is way beyond what we have. Therefore, we redesigned this new model called MCUNet that reduces both the model size and activation size. So MCUNet reduces the model size by 6 times and the activation size by 3.4 times. So that we can not only work on those toy examples like classifying bananas, oranges, or apples, but we can work on those large-scale ImageNet classification, 1,000-class ImageNet classification. And this is achieved by co-designing the Tiny Neural Architecture Search Engine, and also the TinyEngine, which is efficient compiler and runtime. So TinyNAS redesigned the design space. It is latency aware, energy aware. Using the once for all network, we can train once, get many networks to fit different microcontrollers. A TinyEngine is co-designed with the model with fully specialization, graph optimizations, memory-aware scheduling, low precision, and other assembly-level optimizations. Therefore, we achieved a big leap on the large-scale ImageNet classification on microcontrollers, from 54% using TensorFlow Lite Micro plus MobileNet V2 scaled to fit the microcontroller. And now using our TinyNAS plus TinyEngine, which is MCUNet, we can the first to achieve more than 70% ImageNet accuracy, top one ImageNet accuracy on a commercial off-the-shelf microcontroller, which is a pretty exciting result for the TinyML community, showing that we can not only run those toy examples, but also those large-scale ImageNet classification, just like in 2012, AlexNet improved the ImageNet accuracy by a large margin. So this is the memory saving compared with TensorFlow Lite Micro, a micro TVM, and ARM's CM6NN. So we picked the four benchmarks: the small cipher network, the MobileNet V2 with multiplier of 0.35 and resolution of 64. We chose this because this can fit this microcontroller, and Proxy's NAS and MNASnet. So on these four benchmarks, TinyEngine is up to 4.8 times smaller with respect to the memory consumption when running the same benchmark. And this is the latency speed-up comparison. For example, running MobileNet V2 0.35 and resolution of 64, TensorFlow Lite Micro is 200, almost 300 millisecond, but we are only 95 milliseconds, so 3 times faster. So this is the comparison of the TinyNAS and TinyEngine on the STM32F746 microcontroller. This is a very popular microcontroller with Cortex M7 architecture with 320 kilobytes of SRAM and 1 megabyte of flash. The baseline model is MobileNet version 2 plus CM6NN. The full MobileNet version 2 cannot fit such a small microcontroller. Therefore, we have to scale the model with multiplier of 30% with a low input resolution of 80. CM6NN can only fit such a low resolution and low width multiplier on this microcontroller. And as a result, you can imagine the accuracy is not satisfying, only 39% top-line ImageNet accuracy. And then we perform the system optimizations, replacing ARM's CM6NN with our TinyEngine. TinyEngine is memory efficient, therefore it can fit a larger model and also with a larger input resolution. Rather than fitting only 80 by 80, we can now fit 144 by 144 with a larger width multiplier of 0.35. And this result improved the accuracy from 39% to 49%. And next, we perform this model-only optimizations, keeping the same CM6NN, but replace MobileNet version 2 with our TinyNAS. TinyNAS can specialize the neural network for the target inference hardware inference library, and it effectively improved the accuracy to 56%. And finally, we co-designed the TinyNAS and TinyEngine, which boosted accuracy to 62% on the same microcontroller, higher accuracy than the AlexNet. So how do we design this TinyNAS? So we use the neural architecture search to automatically find this efficient model. However, this used to be very expensive. Neural architecture search can emit as much carbon as 5 cars in their lifetimes. It is non-affordable. We propose this approach to decouple training and search using this once-for-all network by weight sharing. Conventional NAS, outside this training forward and backward for loop, there is a microcontroller, there is a search loop. And for different devices, there's another for loop outside it to find a specialized model for each different device, which is for different device, the optimal model is different. Therefore, there are two more for loops outside the already very expensive forward and backward loop. That's the reason that conventional NAS algorithm is very expensive. The once-for-all network decoupled training and search. So we just train only once to do forward and backward, and then we obtain one single model. This process takes 2 to 3 times longer iterations. However, this is one-time cost, which can be effectively amortized across many search scenarios. For example, on different devices, different latency constraints, different accuracy constraints. During the search process, we directly sample a subnetwork from this once-for-all network, which is lightweighted. There's no retraining needed at all, since we can just sample the network, subnetwork, and it can operate independently for each subnetwork. So this doesn't require any training and is very efficient. In this way, when adding a new hardware platform, a new search demand, the marginal search cost is very low, so more than 1,000 times lower search cost, lower marginal search cost, and received the 6 first places in top competitions in efficient AI. And then comes the question, how do we handle diverse microcontroller platforms? So it's highly possible we want to fit a diverse range of product line of microcontrollers. It's very diverse, ranging from Cortex M7, M4, M0, with different memory resources, 512 kilobyte, 320 kilobyte, 256 kilobyte. It's very challenging to design different models for different platforms. It will be an infinite amount of work. So we use this once-for-all network. We can sample a larger network to fit a Cortex M7 microcontroller, and we can sample a smaller subnetwork that can fit a Cortex M4 microcontroller. So this doesn't require any retraining using this once-for-all network. We train once and get many. And the key idea is by weight sharing and progressive shrinking. As a result, this is very similar to the Russian doll, where smaller child networks are nested in larger ones. We can directly pick those child networks without any retraining to directly deploy it. And the accuracy is even better than the child network trained from scratch. This can also efficiently handle different battery conditions. Like for full battery, we can deploy a larger subnetwork. For low battery, we can deploy a smaller subnetwork. So in this way, we can just use one model, once-for-all network. We pick different subnetworks and can fit diverse microcontrollers from STM32F412 with 256 kilobytes of SRAM all the way to STM32H743, which has 512 kilobytes of SRAM. And this is the first to achieve more than 70% ImageNet top-line accuracy on commercial microcontrollers. A big improvement over the existing industry standard. So this once-for-all network not only work for those microcontrollers, but also for mobile phones and also cloud devices. Not only general purpose hardware, but also specialized accelerators like on Xilinx FPGAs. For example, we can see the bottom right image. This is measured on Xilinx ZU3EG FPGA with batch size of 1, 8-bit quantization. The x-axis is the latency, the y-axis is the top-line ImageNet accuracy. So we can reduce the latency from more than 6 milliseconds to only 4 milliseconds, compared with the blue line, which is the mobile net. We can achieve even better accuracy 69.6 versus 69.0. And this method also outperforms the ImageNet by a large margin. So with 80% top-end accuracy, this is 2.6 times faster to inference on this Google Pixel 1 phone on this compared with the ImageNet. Or with the same inference latency, for example, here is 150 milliseconds, the once-for-all network is 3.8 times higher accuracy. And the most amazing stuff is we can train once and get many. So this is a very densely populated trade-off curve. Okay, rather than conventional method, we have to train 4 times to get 4 different models with different latency constraints. But rather, we can get a very smooth, densely populated trade-off curve using this once-for-all network, which greatly improved the productivity of designing different models with different latency and accuracy trade-off. So this is the big picture comparing the computation on the x-axis and the accuracy on the y-axis for many popular neural networks. So on the left, the top, the better. So we can achieve 80% top-line accuracy with less than 600 millimax. And you can observe that all these methods, these models on this corner are done by AutoML or neural architecture search, showing that in general, neural architecture search outperform this human design by a large margin. And once-for-all network is even better than the existing neural architecture search solutions with respect to both the search cost and also the inference latency. And this approach received a couple of awards, including the 3rd, 4th, and 5th low power computer vision challenge on the CPU, DSP, and FPGA diverse hardware platforms, classification task, detection task, visual vigorous task, semantic segmentation task, 2D and 3D, and also NLP track, the language modeling task. So we not only searched the neural architecture, but in this recent DAC conference, we are going to have this paper called Neural Accelerator Architecture Search, also called NAS. We not only search the neural architecture, but also the accelerator architecture. We not only find those hyperparameters, which is those numerical hyperparameters, but also those non-numerical parameters, such as the connectivity and also the loop orders. With this co-design, we can improve the normalized energy delay product step by step. First, using the hardware architecture search only, and then the accelerator architecture search, and both neural architecture search and accelerator architecture search give the optimal optimal energy delay product given the same resource. So let's now talk about applications. So given these powerful TinyML tools, we enabled many TinyML applications. For example, ImageNet, that's very general. And then we have this visual vigorous detecting if there is a person or no person. And also we can do object detection on microcontrollers. We can also do speech command on these microcontrollers. First of all, any questions so far? No question, let me just continue. On the visual vigorous data set, we have three baselines, the MobileNet V2, the Proxylase NAS, and our previous winning solution in the vigorous challenge in CVPR 19, which is on the top right corner. The left is the trade-off between accuracy and latency. The right is the trade-off between accuracy and peak memory. So the MCUNet is 2.4 times faster and 3.7 times smaller compared with existing work, including the MobileNet V2. On the speech command dataset, the audio wake words task, the MCUNet is up to 2.8 times faster, or with 2% higher accuracy compared with the MobileNet, or 4x smaller compared with the MobileNet v2. So the dashed line is the memory constraint, 256 kilobyte of memory constraint. And we can see the MCUNet can fit this 256 kilobyte of activation constraint with pretty high accuracy. So here is a demo for visual wake words, detecting if there is a person, then it's in red. If there's no person, then it's in green. This is not a challenging task, but the challenging part is the small hardware resource that we have, only 320 kilobyte of SRAM and 1 megabyte of flash. We can easily do such tasks on a GPU, but very challenging to do it at high frame rate on this microcontroller. For example, Google's MobileNet plus TensorFlow Lite can achieve only 2.9 frames per second with 75% accuracy. We boosted the accuracy to 87% and the frame rate to 7.3 frames per second by such algorithm and system co-design. Algorithm means the TinyNAS, system means the inference library called TinyEngine. Not only such simple classification task, but also we enabled such object detection task. On the same STM32F746, this tiny microcontroller, we can detect faces and masks. If there is a mask, then it's in green. Or if there's no mask, it'll be in red. The frame rate is pretty satisfying given such a low memory constraint and such a cheap microcontroller for those IoT devices. For example, you can count the number of persons in a restaurant who is wearing a mask, who is not wearing a mask, and to limit the social capacity of an indoor scenario to prevent people gathering with such a low-cost device. And you don't have to send everything to the cloud to provide to protect the privacy for a restaurant, for example. Next, we also enable this person detection on this microcontroller. Again, this is not challenging on GPU at all, but pretty challenging on such low memory consumption, tiny microcontroller. You don't need to pay the high cost of purchasing a hardware accelerator, but just grab a very cheap microcontroller. You can do this smart IoT applications very easily on the microcontroller. Both the indoor and outdoor person detection. And also grocery shelf detection. Imagine you have a robot and want to detect which aisle, which row, how many items are sold, how many items are still there. This model is only 37 kilobyte compared with the MobileNet v2, 3.5 megabyte. We also worked on TinyML for point cloud. So we think autonomous driving is a very important application for edge AI. And for AR and VR, people used to have a whole backpack of computers, self-driving cars, a whole trunk of GPUs, and mobile phones. Now they have a LiDAR scanner since iPad Pro 2020, but again, they are battery constrained. Therefore, the efficiency of LiDAR perception is very important. So on the same hardware platform, the NVIDIA Jetson, we improved the frame rate from 3.4 frames per second to 9 frames per second. And it ranks first on the semantic kitty leaderboard upon publication. So we deploy this model on a real-world full-scale vehicle. So the challenging part is the point cloud is very memory intensive, 2 million points per second, and it's very sparse. The baseline Minkowski-net from NVIDIA and Stanford runs 5 frames per second. With our GPU optimization targeting sparse kernels called Torch Sparse, which is our library, we improved the speed to 18 frames per second. Together with the fast LiDAR net neural network design, efficient neural network design, we improved the frame rate to 47 frames per second. And now it's beyond real time and can drive a car. We also find another computationally expensive application is GANs. So GAN is pretty big. It can do very fascinating image translation, but it's pretty big and pretty slow. Our baseline model runs 12 frames per second on NVIDIA Jetson Nano, but we accelerated to 40 frames per second, 3 times faster, and reduced the flops by 16 times. The FID is even better. So lower FID means better result. Baseline FID 61, ours is 53. The lower, the better. And this is showing the image synthesis. So with 100%, so 1.3x reduction, 1.7 times reduction, 59%, 39% of the computation, even 19% of the computation, we find the image quality is still pretty satisfying, although we already have 5.2x reduction of the computation. So with such technique, we can deploy those GANs locally on our laptops, not yet on microcontrollers, but we're already able to move it from GPUs to only CPU-only desktop, CPU-only laptop, MacBook. So running on this MacBook, the quick edit takes only 0.6 seconds. So pretty interactive. You can finally use finalize to render high quality images. So here we project the original image to a latent space, and we can tweak the hidden vector to generate images, for example, with more smiling, less mustache, etc. We also worked on TinyML for natural language processing. So NLP, such as efficient machine learning machine translation, is a very popular mobile AI application. So we reduced the latency by 3 times on this Raspberry Pi. And with this work called hardware-aware transformer, published in ACL 20, we reduced the model size by up to 25x without losing the BLEU score. We also built a hardware accelerator for the NLP to make it run faster and also reduce the redundancies. The motivation here is that the attention layer in natural language processing is the bottleneck for end-to-end performance, just like the convolution layer for image recognition. The main idea is to reduce the redundancy. Like images, natural language also have a lot of redundancy. Say, given the example below, as a visual treat, the film is almost perfect. In order to classify the sentiment, I only need to keep 5 tokens rather than 11 as treat film perfect, or even just two tokens film perfect. We can still classify the sentiment, it is positive. And this can reduce the computation to only 12% of the original model. So we provided hardware support for this cascaded token head pruning. So the deeper the layer, the less the computation, cascaded token pruning. And also progressive quantization. So we progressively fetch the MSB. If it's very significant, then we can just ignore the LSB. Otherwise, we continue to fetch the LSB. So combining these two methods, so with the specialized data path that brings 22x speed up, with cascaded token and head pruning, it introduces 3x speed up. With progressive quantization, another 2.8 times speed up. All right, and next is TinyML for video recognition. So both 3D point cloud and video are 3D, adding the time dimension or the Z dimension. This is used to be computationally expensive, but we can accurately predict the action and also what happening. Like frame, those corresponds to move something away. The first, second, and third frame and the corresponding spatial region, those are corresponding to move something away. And let me show some speed up running these video recognition tasks. So for the i3D model used to run 164 milliseconds per video, accuracy of 41%. The TSM, our approach, only 17 milliseconds per video, so 9x speed up. Not only the latency, but also the throughput. So the baseline model is running 6 videos per second. So each row corresponds to a bunch of videos. And you can see the right-hand side, the video, the throughput is much higher than on the left-hand side. So 12 times higher throughput. So far, we talk about inference, okay? So we not only want to allow inference on these edge devices, but also we want to do on-device learning. We want to constantly update the model given the new data collected from the user. These data, either speech or images, might be sensitive. So we don't want to upload the data to the cloud to do on-device learning or lifelong learning, but be able to process these data locally or federated learning. Okay? So this used to be challenging because the activation is the bottleneck for forward and backward, especially the backward. You have to store those intermediate activations. So people used to only do those simple tasks like input method, do federated learning on input methods. We want to enable more challenging lifelong learning, on-device learning. So we propose this tiny transfer learning that reduced the training memory from 300 megabytes to only 16 megabytes. And this is achieved by a smart observation that weight bias is memory expensive. And weight update is memory expensive, while the bias update is very memory efficient. In this figure, in the forward, A plus 1 equals to AIW plus BI. In the backward, if we don't need to update the weight, but only update the bias, we don't need to store those intermediate activations. Using this, we can drastically reduce the memory consumption. No need to store those intermediate activations. However, this reduces the accuracy. To compensate for that, we added a light residual learning branch. So compared with the previous slide, here the hollow region indicates the activation doesn't need to store in memory, but the concrete, the solid color means those activations are stored in the memory. Those light residual modules have only 1/6 of the channels, half of the resolution, 2/3 of the depth. But they can capture those fine-tuning model capacity. That is enough for fine-tuning those models, achieving even better accuracy than fine-tuning the last layer, but give a very small memory overhead. All right, so we talk about federated learning, then we need to talk about the safety of federated learning. So is it safe to exchange the gradients? So here we find it's actually not safe to exchange the gradients. If we share those gradients to the public, people can still steal the input image or input sentence from these gradients. And the idea is on the top left corner, where given input image, pass through a differentiable model, we get a prediction, get a loss, okay, get a gradient. With a randomly initialized input, we pass it through a differentiable model, and then we get a gradient. We can try to match the gradient and back propagate the loss all the way back to the random input and also the label. We try to minimize the difference of the gradients. Therefore, we can learn what is the original input image. On the bottom shows the attack result as different iterations. We can clearly recover this batch of 5 input training images during training, very close to the ground truth. And on the right-hand side, is showing that we can also leak the natural languages from iteration 0, where we initialize everything as garbage sentences, all the way to iteration 50. We can almost fully recover the input sentence. So this is posing a challenge that breaking the people's convention that people used to think the gradient is safe to exchange, but actually it's not. So how can we preserve the privacy while we are doing this edge cloud inference? The idea is the edge may not have all the computation power as always. With complicated tasks, can we process a small fraction on the edge and then offload a large proportion, say 80% on the cloud, and then finally do a little bit post-processing on the edge so that the cloud does not see the original input? A naive solution is to add some noise or blur, to do some blurring of the input image before sending to the cloud. However, those are easily attacked, like adding some noise, given the first row is the input data, the second row is adding noise, the third row is the attacked result by using the GANs. Even blurring, we can easily attack the image by using GANs, since the distribution of phase is learned by the GAN. So even seeing a low resolution image, we can still attack the image. We use a different approach called data mix. We can mix, say, multiple persons' data into one single image. Okay, and then we feed this mixed data to the cloud. It's very difficult to be attacked by both the human and the GAN model. Okay, so the last row shows the attack result using the same GAN. You can hardly tell one from another, so it's dependent. And the second to the last is the model after the data mix. We find it's very difficult to tell which person is which after the mix. Therefore, we can have a very low attack success rate on the person ID, but a very high accuracy on the top left corner on this trade-off between attack success rate and also the attribute classification accuracy. Usually, lower success rate means lower classification accuracy. For example, you can add a stronger blur or lower resolution to have a lower attack rate, but also that decreases the classification accuracy. With our approach, the attack success rate is pretty low, but the classification accuracy is well maintained at a pretty high accuracy. And on the right-hand side is the keyword spotting on the voice data set. So compared with the adding noise with different magnitude, our data mix approach can drastically reduce the attack success rate from 90% to only 13%, but while maintain the classification accuracy to 95%. All right, last but not the least, we also worked on data efficiency, not only computation efficiency, but also data efficiency. Since modern deep learning requires a lot of data, which is difficult and expensive to collect and label. For example, again, training GANs, people used to require 70,000 images on the FFHQ dataset so that GAN can generate photorealistic data. We proposed an approach called diff augment that can use only 100 images to generate those photorealistic data. So without our technique, 100 images lead to very poor quality. But with our diff augment technique, the generated image is very photorealistic. And there are more examples of the generated image trained on only 100 images. It can smoothly interpolate between different seasons and nights, days and nights, and different angles of the face. All right, in summary, today we presented TinyML and efficient deep learning, as well as those TinyML applications on point cloud, video, GANs, and natural languages. We show this principle can be applied to diverse applications. From cloud AI, mobile AI to tiny AI, we feel it's a very promising direction that more and more exciting applications are enabled on these microcontrollers. We can already reach 70% ImageNet top-line accuracy with such microcontroller, which opens the door for many exciting opportunities in the future for these AI plus IoT applications with lower computation, smaller model, faster and greener, and more accessible to everyone. Okay, with that, there are more resources on our GitHub and YouTube channel. Welcome to check out our homepage. And we thank all our sponsors and students for supporting our work. And that's all for my tutorial. Thanks for your attention, and I'm glad to use the next 10 minutes to take questions.
All right. Yeah, I just want to say a very big thank you to Professor Song Han for the fantastic tutorial. You know, it's really educational and impressive. I must say that every couple of months when I meet you again, you always bring me some new surprises. Yeah, so yeah, I can also see the popularity of your talk given the number of attendees in this session. So yeah, so if any of you have questions, please raise your hand or type it down. I do see that there are a couple of audience who have raised your hand, but I don't know if the host can actually give you the control on the mic. So if not, can you type down your question?
I have a quick question. This is a very interesting talk, and also it puts in perspective the requirements of the hardware. And what we see today is that there is a lot of work towards, for instance, looking at the bit width of the arithmetics, or doing in-memory computation, or yeah, this type of really directed research. What is, in your opinion, based on the kind of work that you are doing, what is, in your opinion, the best ideal hardware? How should it look like? Should we be really doing in-memory computation? What do you think should look the hardware?
Yeah, so with I would say first priority is to be flexible. So recently we see a huge opportunity designing new neural network architectures rather than MobileNet, ResNet, etc. So those improvements it's highly possible to outperform those silicon architecture improvements. So flexibility is very important. And secondly, I would say memory footprint, efficient memory hierarchy is quite important. So we find several constraints on existing microcontrollers with respect to the memory versus available memory resource. So if that can be improved, it'll be very helpful.
Thank you.
Yeah, so we have a question here. So he said, out of microcontrollers, DSPs, and FPGAs, which one do you speculate to have popular demand in the future? I think it's a very large question, but you can try your best to answer it.
I see different application scenarios, right? It's hard to tell which one is better. As always, it's a trade-off between the cost and also the performance and also the budget of the power, right? And even microcontrollers, there are M0, M4, M7 with different capacities. For example, if you want to do those time series analysis on the power socket, for example, those time series data can be easily analyzed on M0, M4 microcontroller, right? And with such simple detection tasks, M7 might be, or even DSPs might be a good choice. And also for FPGAs with a slightly larger task like auto driving driving related scenario, it would be very powerful with Xilinx toolchain with the modern Vitus AI. All the model compression tools are already integrated there. The pruning quantization tool is natively supported and have a pretty big model zoo for diverse detection segmentation tasks and other auto driving tasks. So really, Xilinx made it very popular, very easy for everyone to access those pre-trained models. It also depends on whether you want to use those pre-trained models with a push-the-button solution, or you want to design those models, tweak those models on yourself. So there are different approaches.
Yeah, great. We have another question from Junaid. He is asking, when battery is low, it may take more time to do the processing because of smaller DNN. Doesn't it beat the goal of efficiency?
When battery is low, it may take more time to do the processing. Oh, so when battery low, as we show in the previous slide, we can pick a small subnetwork from the once-for-all network. So not necessarily take a lot more time, but also what we want is slightly more time, slightly degrade the accuracy, but use a much smaller and lower power consumption model. So making the trade-off curve to be relatively flat when you are reducing the computation. Just like the demo that we are seeing here for this image synthesis. Let me share the slide again. For the image synthesis tasks, when we are reducing the computation to even from 100% and do 70 to 8%, you can hardly observe the degradation of the quality. Okay, 70%, even 19%, right? The generated image quality hardly degrades. So that's what we want. Given low power, we process a smaller model with less computation, but we want to maintain the quality as much as possible, just like in this demo.
Cool. That's really cool. Yeah, thanks for the answer. Do any of you still have any other questions? Okay, so if there are no any other questions, let me conclude the session. Let's thank the speaker, Professor Song Han, again, and I also thank everyone for your participation. If you have any other questions, you can always shoot him email. Yeah, so a very big thank you to Professor Song again.
Okay, thank you.
Thank you.
You.